just as a well-formed formula like P or Q isn't true or false until you've chosen truth values for the propositional variables P or Q, a first-order formula like for all x, P of x, isn't true or false on its own until we've given some further information. Specifically, what we have to decide is where the variable x is going to come from and what the relation P means. And that data, so choosing a set over which the variable is going to range and a meaning for the relation symbol P, is called an interpretation of this formula. And this video is about interpretations and how, once we've decided on an interpretation, we can determine whether or not the formula is true in that interpretation. Here's the definition then of an interpretation. An interpretation of a first-order formula consists, first of all, of a set to which the variables of the interpreted formula are going to come from, and secondly, for each relation symbol in the first-order formula, a relation on the set A. Now, an important thing about our relations is they're not quite the same as the relations that we used when we were talking about relations in our set theory part, and in the part of this course on set theory. Then we dealt just with relations which were relations between two different things. So a relation was a property of an ordered pair. But we will now think about just relations where they have one input only, and then a relation P of x, once interpreted, will be something which is true or false about a single element x. On the other hand, we might have a three-place relation Px, y, z, which is a statement which is true or false about three different things x, y, and z. So we're generalizing the notion of a relation slightly. Let's look at an example then of an interpretation. So consider the first-order formula exists x, P of x. And again, the interpretation of a relation with just one input is it's a statement about a thing x which might be true or false. So an interpretation for this first-order formula consists of a set where the variable x has to come from. So we might take x to be the rational numbers q, and an interpretation for the relation P might be P of x is the statement x squared equals 2. So that's a statement which might be true or false about a particular thing x. Once we've chosen this set for the variables to come from and this meaning for the relation, the interpretive formula becomes that there exists x in Q such that x squared is equal to 2. And once we've given this interpretation, we can now determine whether or not that's a true or false statement. In fact, it's false that there is a rational number x whose square is equal to 2. So in this interpretation, the formula becomes false. That's the famous fact that root 2 is irrational. So if you've not seen the notation blackboard bold Q before, what it means is simply all the rational numbers, so all the fractions. So we could write it as a over b for all a and b whole numbers where b is not 0. Once we've given an interpretation, we then have to figure out how to determine whether that interpreted statement is true or false. So for well-formed formulas, once you've decided on truth values for the propositional variables, we then developed a procedure that let you figure out the truth value of the well-formed formula under that truth assignment. We want to do the same for first-order formulas. And the problem we've got, or the extra difficulty we've got over well-formed formulas, is these quantifiers, so for all and there exists. On this slide, we're going to think about how to determine the truth or falsity of an interpreted first-order formula that begins with the quantifier for all. We're going to give a definition of how to do that. So the definition is that an interpreted formula which looks like for all x in a set A, something happens. So phi here just denotes the rest of the formula. Such an interpreted formula is true if and only if, for each element little a in the set big A, the statement you get by replacing the variable x by the actual thing A in the remains of the formula is a true statement. Let's explore an example of this. So we'll consider the formula for all x p of x. Possible interpretation of that is taking the set A to be R, so the variable x ranges over the real numbers, and taking the relation p of x to be x squared is greater than or equal to 0. So then the interpretive formula becomes for all x in the real numbers, x squared is greater than or equal to 0. That's true because whenever we take a real number a, and when we substitute that into the remains of the interpretive formula, we get a squared is greater than or equal to 0, and that's a true statement, no matter what a is, no matter what real number a is. So that's the recipe for deciding truth of interpretations of formulas which begin with a for all quantifier. Let's now do the same for there exist quantifiers. So the definition for there exist quantifiers is similar. An interpretive formula that looks like there exists x in the set A, and then the phi here denotes the rest of the formula. Such an interpretive formula is true in that interpretation if, for some element little a of the set big A, the statement you get by replacing the variable x by the element a in the rest of that formula, which I denoted as phi, is a true statement. Let's try some example then of doing this, because it will become a little clearer when we try this. So we'll consider the first order formula: exists n for all m r of n and m. So to interpret that, I have to give a set from which the variables n and m come, and a relation r on that set. So in our first interpretation, we'll choose a to be the set n, and r to be the relation less than. When I do that, the interpretive formula becomes there exists n in the natural numbers. For all m in the natural numbers, n is less than m. Now that's false, and the reason that is false is because you can't find a natural number a such that when you substitute a for n in this statement, you get a true statement. So for, well, let's say there is no a in the natural numbers, making for all m in n a less than m true. Right? No a at all makes that true. The problem being a is supposed to be a natural number, and you can't, no natural number is less than every other natural number, because no natural number is less than itself. So no matter what a you choose, you can't make that into a true statement, and therefore, according to our definition, we should regard this interpreted statement as false. Now let's look at a different interpretation of the same formula. So this time we're going to interpret the variables as coming from the set of natural numbers again, so the same domain of this interpretation, but we'll look at a different relation. So this time the relation will be the less than or equal to relation on the set of natural numbers. This time the interpretive formula becomes there exists a natural number n such that for all natural numbers m, n is less than or equal to m. This is a true statement, so the interpretation of this first order formula is true. And the reason it's true is because there is a natural number a which you can substitute for n in the remains of the formula and make it into a true statement. So if we take a equals 0, then for all m in n, 0 is less than or equal to m is true. So there was an element of our set A such that when you substituted that element For the n in the remains of the statement, you've got something which was true, which means that the interpretive formula is true in this interpretation. So just to emphasize, this gives us an important example that shows that a particular first order formula can be true in one interpretation and false in another interpretation. We saw here that the same formula was true in our second interpretation and false in the first interpretation.